Well, we're coming off a series of videos where we've been talking a lot about exponents and how to simplify and manipulate and rewrite all these different exponents. And that naturally builds us up to this point today where we can dive into exponential functions. And the key characteristic to an exponential function is a function where the base is a constant now as opposed to a variable, okay? And now the exponent contains the variable. So if we can meet those two criteria, then we've got ourselves an exponential function. And that's really where we want to end up here today. First and foremost, we want to be able to look at a list of functions and determine which ones are exponential and which ones aren't, and be able to explain or justify why we think that way. Okay. And then we're going to get into a lot of graphing, and we're going to finish off today's video with a nice, concise list of all of the key characteristics of these exponential functions. And they generally do take on the same shape. And so, the difference between 2 to the x versus 3 to the x versus 4 to the x is very minuscule. Just really the rate at which they increase is the only significant difference in my mind. So exactly what is the definition of an exponential function? Okay, we're saying it's got a base of b, okay, and it's either going to be written like this or with y equals, okay. Now, here's what you want to highlight in your notebook. The b has got to be a positive constant, okay. It's got to be a 2 or a 1/2 or a 3 or a 1/3. It can't be -2, can't be -3, can't be -1/2. It's got to be positive, and it can't be 1 either, okay. It's either got to fall between 0 and 1, or it's got to be bigger than 1. And hopefully we'll get a chance to explain why that is. And then, of course, x is a variable that represents any real number. So we have some examples of exponential functions. And what you'll notice as you look at this list, okay, the base is positive, and you got a variable up top, right? Base is positive, variable up top. Base is positive, you got a variable sitting up top. Base is still positive. It's okay. It's a fraction. As long as it's positive and as long as it's not 1, we're okay. And then you got your variable sitting up top here. All right. Now here are some non-examples of exponential functions. And this one's just flip-flop. They got the variable on the bottom and the constant up top. We want to just reverse the two. Here, you can't have a 1, right? And the reason is 1 to any power equals 1. So the output would always be 1, and you'd end up graphing a straight line. If x equals 2, the answer's still 1. If x equals 3, the answer's still 1, and you just get a flat horizontal line. Okay. The problem on this third example is the negative base. That's no good. And the problem on the fourth example is this variable base right here. So the base has got to be a positive constant. Cannot be a variable like we see there. So which of the following are exponential functions, okay? Maybe take a moment, hit pause, just think through this for, 10, 15, 30 seconds of your own time here. I think I like this one here because the base is a positive constant and we got the variable up top. And I like this one here. Again, I've got a positive base and the variable sits up top. The problem here is we've got the variable on the base and the constant up top. So we can just gotta flip those two. And then here we've got a negative base, which we've got a problem with. So we don't like those two examples right there. The next thing I want to do is talk about creating a table of coordinates or a table of values to graph these functions. And if you're thinking, geez, why don't we, this is why we got calculators, right? Why do I got to do this by hand? Well, it's just like, hey, if you really want to know how a car operates, you gotta open the hood. You gotta roll up your sleeves. You gotta get your hands a little dirty. We gotta know how that engine really does what it does. And so we're gonna go a little Vin Diesel here and Fast and the Furious and try to juice up our own car. We're gonna try to juice up our own functions and try to really understand how they operate and why they do what they do. So first and foremost, I'm actually gonna start with the -3 right here. We'll come back to the -30 in a second. 2 raised to the -3. You know what? I don't like that green too much. I don't know if I'm going to like this one any better, but we'll try 2 to the -3. Oh, yeah, I like that. 1 over 2 cubed makes 1/8. Let's see if I can blow this picture up a little bit so I can get those boxes are just a little too small for me. All right, let's go with that. All right. 2 to the -2 makes 1 over 2 squared, which makes 1/4. 2 to the -1 makes 1 over 2 to the first, which makes 1/2. 2 to the 0, just like anything to the 0, makes 1. 2 to the first makes 2. 2 to the second makes 4. 2 to the third makes 8. All right, now let's take a moment and try to take care of that x equals negative 30, and then we'll jump down to the bottom and take care of x equals positive 30. So if I did 2 to the negative 30th, or 1 divided by 2 to the positive 30th, my calculator says, check this out, 0, 0, 0, 0, 0, 0, 0, 0, 9, 3, 1, da, 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 da. Now, the point of me doing that is to emphasize, like, listen, I still got a positive answer, but it is really, 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 really close to 0. So that's what we're saying is we're getting really, really close to the x-axis, but we're not quite touching it, right? Now, what about 2 to the 30th? Let's pump that bear into the calculator. I bet this is going to be a big number, eh? Okay, 2 to the 30th. Let's see if I can copy this down. 107,374,1824. Let's check this out. Put some commas in there. So 1,073,741,824. So my point there being is these numbers are going to get ridiculously huge, okay, as x increases here. So I'm just going to take a moment. We'll try to plot these points as carefully as I can. It's going to be tough because like 1/8 is really small. 1/4, 1/2, 1, 2, we got a 4, and then we got an 8. So let's see if we can shrink this page back down a tick. Okay, so we'll get our 8 in there. So this function is going to be asymptotic to the x-axis, which means it gets closer and closer and closer, but never touches it. Oh boy, I screwed that up. Let's go through here as smooth as we can. That's tough with the stylus. We got to practice a little bit more. So that's what my exponential function is going to look like. Notice we do have a y-intercept of 1. It approaches but never touches the x-axis, which basically creates, let's see, I can change the pen size here. We've got what we call a horizontal asymptote right here along the x-axis at what we call y equals 0. All right, let's take a look at another example. So what happens if I do 1/2 to the x? All right, we'll try a similar process. And again, I'm going to skip that negative 30 for the time being. I'm going to go with 1. Whoa, got to shrink that pen size or I'm never going to get this in there. 1/2 to the negative 3 becomes 2 to the positive 3. So you get 8. Then we got 1/2 to the negative 2, which is 2 to the positive 2. So again, I guess what you're seeing me do here is if I reciprocate the base, it's going to change the sign of that exponent and you just get the 2. Anything raised to the 0 is just going to be 1. 1/2 to the first is 1/2. 1/2 to the second makes 1/4. 1/2 to the third makes 1/8. And then we'll grab our calculator. We'll try. So 1/2 to the negative 30th is going to make 2 to the 30th. That's going to be the same gigantic answer we got up top. So it's like 1 billion. So this graph is going to start huge, and then he's going to finish really small because 1/2 to the 30th is going to be that 0.000000009 number. So we're going to finish positive by a whisker. All right. So if we start to graph this, negative 3 makes an 8, negative 2 makes a 4, negative 1 makes a 2, and then a 1 and a half and a 4th and an 8th. And we'll say, okay, it's a little better so far. Don't jinx it, Hill. Oh, yeah. Much improved. I like that curve a lot better than my previous one. Now, notice that this function is now decreasing as opposed to the last one was increasing, right? We still cross the y-axis at 1, ironic enough. They share the same y-intercept, but we're still asymptotic to that x-axis. So we've got y equals 0 as our horizontal asymptote. Now, we could continue to graph some more, and I'd love to, but I want to try to keep this video under 5 hours if we can. So we'll kind of generalize some basic things here. These are all the characteristics of an exponential function in the form f of x equals b to the x. So in other words, what does that mean? What's so special about this form? Really, what I want to emphasize is we're not performing any transformations or shifts yet. We're not shifting the function up, down, left, or right. We're just, it's 2 to the x, or it's 3 to the x, or it's 1/2 to the x. It's something to the x. And so you either get an increasing function like we have here, and in that case, your base is going to be greater than 1, okay? Or you're getting a decreasing function where the base is still positive, but it's less than 1. So it's going to fall somewhere between 0 and 1, but it can't equal 1. Remember that from up top. Okay, so here are all the common things we want to be comfortable with. We're going to say our domain is all real numbers. We extend infinitely to the left, infinitely to the right. Our range is going to be all positive real numbers. In other words, 0 and above. They all pass through the point 0, 1 because any b value raised to the 0 power must equal 1. That's how you end up with the same y-intercept for all these functions. Okay, something we kind of already hit on. If b is bigger than 1, the function's going to increase. All right, and then the greater the value of b, the steeper it gets. So 4 to the x is steeper than 3 to the x. 8 to the x power steeper than 7 to the x. And then conversely, if b is positive but smaller than 1, now the graph is going to decrease. And this is an interesting one to think about. The smaller the value of b, the steeper it gets. Okay, so I want to pause right there for a second. So let's say I have 1/2 to the x, and maybe I have 1/10 to the x. Which one's going to be steeper? Which one's going to be steeper? Actually, 1/10 to the x is going to be steeper because we just said the smaller the value of b. 1/10 is smaller than 1/2, so that's going to be the steeper one. Okay, here's some other stuff that's going to separate you from the crowd. We talked about, one of the dual purposes here, besides getting really good at Algebra 2, is kind of preparing ourselves for things like the SAT, right? And this, things like this may separate us. These functions that we're graphing here today, they're all 1-to-1. What the heck does that mean? What does it mean to be 1-to-1? It means the functions, they not only pass the vertical line test, but they also pass the horizontal line test. They pass both of those tests, and that guarantees that the inverse of these functions is also a function. We're going to get into that in a couple of days. And then as far as the asymptote goes, we'd say these graphs, they approach but do not touch the x-axis, and hence y = 0 is our horizontal asymptote. Ladies and gentlemen, that's everything we need to know tonight. Hope you appreciated lifting the hood and taking a look underneath to see how these bears really operate, and we'll catch you later.